All right, so we're gonna wrap up 13.4 today. I'll have the homework assignment for you. It's at the end of this section. I'll show you those, and we're going to start 13.5 today. Hopefully, get through most of 13.5. If there's a chance, we might start 13.6. 13.5 is pretty short. Okay, but we need to finish up 13.4, which was Green's theorem, right? So let's say that I have some interest in figuring out the double integral over this region D, but this is not a simply connected region. Remember, I said if you take out the center of it, then that's not anything we dealt with. You can't shrink it down, can't shrink a curve down through that hollow part, that hole. All right, so but we're going to investigate this, and we're going to get a pretty amazing result when I'm done with this, all right? And then we're going to be able to answer a pretty, like what appears to be a very difficult question. We're going to be able to do it with pretty good ease, I guess. All right, so see the region? I'm going to take that region right now, and I'm going to come in and I'm going to cut it. So I'm going to cut it here and just here. And that's going to create two regions, which I will call D1 and D2. All right? I am also going to define two paths on this object here. The first path is going to go in this direction, counterclockwise, which is positive orientation or negative? Positive orientation is counterclockwise. I'm going to call that path C1, okay? I'm going to define another path. I'm going to have to use red because I'm running out of colors here. Another path which is going to go around the smaller inside part, and I'm going to orient that clockwise. All right? Got it? And that's I'm going to call this C2. So I have a big region D, which I'm going to cut into two pieces, and I'm looking at two curves on that region, one that goes around the outside and one that goes around the inside. One of them is positively oriented, the other one is negatively oriented, right? Now imagine that I actually physically come in here where I cut that and pull these two apart to put some space between them just so we can look at them, all right? Now, I'm not going to be able to do an exact copy, but I'll do my best. All right, the top region goes something like this. I cut it here, and then it goes like this, like that, and then the bottom one, something like this, comes over here, drops down, right, goes like that. Yes? You agree? All right, now I'm going to put some points on here. Here, 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 here. And I'm now going to label some paths on this, all right? Not those paths, not C1 and C2. I'm going to call these different things, all right? I'm going to look at the path that goes this direction, like this, comes all the way back around, right? That's a nice closed curve, isn't it? Let's call this first piece right here, just this path that goes from this point to this point, let's call that E1. Let's call the path that goes all the way around like this to that point, let's call that E2. The path that goes from here to here, let's call that E3. And the path that goes in this little kind of circular shape here, E4. You with me? The region inside, remember, this piece in here is D1, isn't it? That's D1 inside. Now I'm going to label another set of paths on this one. And it's also going to be the same, actually opposite orientation. Hold on a second. Yeah, let's go opposite. So like this. Sorry, I'm saying opposite. Just ignore what I'm saying. I'm saying the opposite of what's happening here. So let's do it positively oriented like this. Okay? With me? I'm going to call this little piece from here to here, call it F1. Call this F2. call this F3, all the way back around F4. Okay? We all right with this? All right. What I'm interested in is the double integral. I'm going to use Green's theorem here. The double integral over D, partial Q with respect to x minus partial P with respect to y. That look familiar? Yes? That should be equal to the double integral over D1 of the partial Q with respect to x minus partial P with respect to y dA, what? Plus double integral over D2 partial Q with respect to x minus partial P with respect to y dA. We agree with that? That's just the fact that when you do a double integral over a region D, that if those regions are connected together, you can do them separately, right? So that's fair. But by Green's theorem, this integral right here, just this one, this double integral, should be equal to the line integral, right? Green's theorem, the line integral along the curve that encloses D, as long as that curve is in the positive orientation. So notice that this is positively oriented, right? So this right here, just this, should be equal to the line integral over this whole path. But since I broke it up into smaller paths, do you agree I could say line integral over E1 of, what is the formula? P dx plus Q dy. All right? Then plus, hold on a second. Yeah, E2. So I'm moving here to here. Now go around here. That's E2. So plus integral E2 P dx plus Q dy plus what? E3, E4, right? To save room, I'm just going to put integral E3 blah plus integral E4 blah, right? Same thing I had over here. All right, that's this one. Plus this one, which should be, now I'm moving around D2. Here's D2. It's positively oriented, right? So I move around that one. And when I move around that one, I'm going to have line integral over what? Let's start at F1, okay? F1 of the same thing, right? P dx plus Q dy. So blah plus what? F2 blah plus F3 blah plus F4 blah. Yes? Everyone agree with this? All right, anyone see anything interesting in here? I'll give you a hint. Do these cancel? Do these cancel? They're opposite directions. Do you notice that E1 is the opposite direction of F1? In line integrals, if you change the direction, you get the same answer but negative. So this integral right here over this path should cancel out with the one over F1. And E3 should cancel out with what? F3. And what's left is pretty amazing, I think, if you see it. What is E2 and E4, right? That's what we have. F2 and F4. So let me do it this way. I have to erase here. Remember, that's what we're looking to get, right? That's what we wanted to see what it turned into. This should be, I want you to look at E2 and F4. What's E2 and F4, those two paths put together? Which is C1. That's the outer one, right? That's C1. So this is just the line integral over C1 of P dx plus Q dy, right? Plus, now, what's the others that are left? What's E4 and F2? Where is it? C2, right? It's this right here. E4 continuing on to F2 gives me C2. Understand? P dx plus Q dy. That's it. Okay, now that may not seem like a big deal, but it's going to help us out here quite a bit in just a second. What it's saying, what this whole derivation is saying, is that if somebody gives you a region, right, and you have this curve that goes around it, and you punch a hole out of the middle of it, and you have another curve that's oriented opposite, right, that the relationship between the double integral over this region and the line integrals enclosing the two little loops here is this. Okay? That's pretty cool. All right, now let's move to the example. Now I put that in my notes, okay? In the notes that you print offline, but I did it a little different in my notes online, and it's harder to follow, I think, than what I just put up here. I hope. If you've looked at my notes, I don't go in as much detail with the notes. I don't break it up as E1, E2, E3, E4, F1, F2, F3, F4. So it's harder to see that cancellation happening. I just kind of say, hey, look, these cancel. They're opposite directions. So just remember this, all right? Now, how can we use that result? So look at this question. Show that the line integral of the vector field f dot dr, which could represent work, right? This could represent work. It's not necessarily in this problem, but what is the line integral of the vector field f dot dr over the curve C, right? Show that that is equal to 2 pi for this vector field where C is any closed path enclosing the origin. So that's saying if I take the xy plane, here's the origin. If I draw any path, right? Any path. Ooh, I need to throw that away. Okay, heads up. All right. Oh, that was total luck. See, I kind of stretched out first. All right, so if I take any path, any closed path that encloses the origin, that if I do the line integral over that path, it's going to be 2 pi. But the key word in the problem is that you're supposed to show this happens for any curve. So how can you possibly ever do that, right? I mean, you can't check all the curves that enclose the origin, can you? You can't. I'm about to use what we just derived a second ago, all right? And here's the way I'm going to do it. First of all, let's just call this path C, all right? And I'm going to have positive orientation on this path. Let's call this C. I'm not going to call it C1, all right? I'm just going to call it C. That's this path. That is an arbitrary path, right? Then I'm going to come in here and very cleverly, if that's a word, I'm going to choose a positive number, A, such that the circle with radius A is inside C. Do you think I can do that? If somebody draws a curve, right, any curve, where the origin is inside of it, but not on the edge of it, right? Can I choose a small enough circle so that I will be inside that curve? Yes? Because, yes, the answer is yes. And the reason is because if this curve does not touch the origin, then there's some gap between the origin and the curve, right? And I can always choose my A to be half that distance. And I'm never going to run out of positive numbers that are greater than 0, right? So I can always fit this little, later on if you actually study math, we call these little epsilon balls. If you can fit a little epsilon ball inside of here, then I can do it, right? Yes? No one's going to argue with me on that?
What if it's on the curve, or like the curve goes through the origin?
Okay, so that's why it says it encloses the origin, and what we mean by that is that it is not on the curve itself. It doesn't say it explicitly, but just so we understand, that's what they mean. All right? If it lives on the curve, that's a different story. The origin is on the curve. Okay, so let me draw this little circle that I'm going to put in here. And just so you can see it, the A might be smaller, but that circle's right here. It has a radius of A. You with me? I'm going to orient that the same direction. I know in the previous thing where I was deriving the formula, it was the opposite direction, but I'm going to do this in the same direction like that. And I'm going to call this C. You want C1 or C2 or C sub A? What do you want? C1? I heard C sub 1 first. Is that okay? So we have C is the big one, right? That we started the problem with. It's an arbitrary curve. And I'm coming in here and I'm constructing a smaller circle inside that curve. With me? Okay. What can I do next? Let's talk about what the line integral over C of f dot dr plus, let's just look at what this is, plus negative C1 of f dot dr would be. I do realize I put a negative here. That means I'm going to reverse the direction. Okay? Well, this, by the definition of this is C P dx plus Q dy plus this C1 of P dx plus Q dy. Do you agree with that? If you did the bonus problem, you know, I think, that this is equal to this. Okay? That this is equal to this. And can you tell me what that is? So look, what does negative C1 look like? It's the same curve, but the opposite direction. Do you agree with that? So everyone agrees it's that in the opposite direction. Isn't that what I just had on the board a second ago? Didn't I do that? If you had this region D, I cut out a circle. I said this way on this one on that one, right? And we said that this really makes this equation true. It says this was C1, this was C2. Said line integral over C1 of blah plus line integral of C2 blah would be equal to double integral over D, right, of the partial stuff. Well, this C goes positively oriented. This negative C is negatively oriented, just like in the formula here. So shouldn't this turn into Green's theorem? Yes? Okay, so keeping that equals going, okay, keeping the equals going here, this should be equal to the double integral over what? The entire thing, right? The entire thing, that's D. right? Or is it without the circle? Hold on. I did too much. What was D in the last one? This right here. D was the region between them, sorry. Yeah, so not including this, right? You all okay with that? Of what? Partial Q with respect to X minus partial P with respect to Y, D, A. Yes? We're all